go unanswered for some years to come. In the meantime, however, seemingly unrelated global events prompted scientists around the world to revisit the theory that for decades had consumed Alfred Wegener.
I really think our understanding of the oceans came out because of World War II, ironically. Because in World War II, a lot of new technology was developed. It was mostly for submarine warfare. So we needed to know the landscape down there, and we needed to be able to detect metal under the water.
They developed the ability after World War II to start doing precision depth recording, so they could actually do soundings of the ocean floor with something other than just a line with a rock tied to the end, or something very primitive that took a long time. So once they had echo sounding, they could actually start surveying the ocean floor, and they could see that there were these underwater trenches and mountain ranges, and that where they had underwater mountain ranges sometimes correlated to where they had the earthquakes. And the sort of systematic surveying of the oceans, I believe, started around or about after World War II.
In 1960, Princeton scientist Harry Hess and Robert Dietz of the Scripps Institution of Oceanography proposed a radical new idea to explain these unexpected features that had been discovered at the depths of the ocean. Known as seafloor spreading, this bold hypothesis proved to be of staggering importance. It suggested that new seafloor develops at oceanic ridges, or spreading centers. According to the Hess-Dietz theory, as this new seafloor spreads out symmetrically to either side, it carries along with it the continents whose movement Alfred Wegener tried to prove decades earlier. While the notion of seafloor spreading was well received, scientists still needed additional proof to demonstrate its validity.
As part of the effort in World War II, we developed magnetometers that you could pull and see if there was a magnetic object under the water. And they developed very good sonars to figure out the depth of the ocean. And after about a decade, we had collected enough data to see the basic structure of the oceans and to pick up their magnetism, which turned out to be a crucial key in the whole thing.
In 1963, geologists Frederick Vine, Drummond Matthews, and Lawrence Morley noted that magnetic residue locked in the rocks on the ocean floor had apparently been laid down over time in strikingly symmetrical patterns on either side of oceanic ridges. They also recognized that these patterns coincided with known reversals in Earth's magnetic field that have occurred periodically.
When they were measuring the magnetic field of the Earth, they discovered that it reverses. That for a while the North Pole will be at the north, so if I had a compass here it would point north. But at other times the field dies down, and when it grows again it can be pointing either direction, north or south.
People were measuring rocks that they had collected on land. And they found, since the early 1900s, rocks that were magnetized in the wrong direction. They were pointing south, not north. And most rocks, if you heat them up, I'm talking about igneous rocks, so rocks that have come out of a volcano. They're completely different than sedimentary rocks. They start their life very hot. When you do that and then you cool them in the presence of a magnetic field, they become magnetized in the direction of the magnetic field. And these rocks should have been pointing north, and they weren't. They were pointing south. So what was going on here? Either the magnetic field completely flipped, which nobody could conceive of, or there was some complicated phenomenon called self-reversal. It was very bizarre. Or the entire crust had flipped over. I mean, something weird was going on. So in order to test what had actually happened, some people went around all the continents, got lava flows that had been extruded over the last, say, 5 million years. These were dated with a new technique at the time called potassium-argon dating. It uses radioactive decay, and it was pretty new to be able to do this in the early 60s. It took a long time to develop the technology to be able to do this. And they found that rocks all over the world that with the same age had the same polarity. They were pointing north if they were less than, say, 800,000 years old, and they were pointing south if they were 1.5 million years old.
You know, you might say, well, so what? turns out that's perfect for proving seafloor spreading. When that ground comes apart at a seafloor spreading center, the lava that comes in is basalt, that black lava, and it's full of little crystals of magnetite. And when they cool, they get magnetized in whatever field happens to be there at the time.
And if the Earth's field was reversing polarity and the rocks were recording those reversals in polarity, it would serve as kind of a barcode recorder, a symmetric barcode recorder of that history of opening of the ocean basins.
So there are whole stripes of seafloor that are magnetized in one direction and then the other. And they're symmetrical, good for seafloor spreading, and they have a very distinct pattern of widths, which is just dependent on how long each of those intervals of normal or reverse magnetization lasted. And so it's a very, very distinct pattern.
What you find is a very regular, astoundingly, astonishingly regular pattern of highs and lows, which make these long stripes. If you color all the highs black and all the lows white, what you find is these, what they call lineated magnetic anomalies, which make, they're also known as zebra stripes because that's what they look like. The people who were studying the seafloor suddenly said, oh, that's it. It was one of those eureka moments, because if you have seafloor being formed at spreading centers and spreading out in the presence of a reversing field, you'll get magnetic stripes.
So it's kind of a tape recorder of the reversals of the magnetic field throughout time. And that's kind of proof for the evidence of seafloor spreading.
The implications of these magnetic markers for the seafloor spreading hypothesis were profound, but there was still more work to be done.
The evidence for seafloor spreading includes the magnetic anomalies, but it also includes this concept of how much sediment accumulates on the ocean floor and how old the sediments are. Because the idea is that if you're creating new seafloor at the spreading ridge and then the plates are moving apart, as the seafloor gets away from the spreading ridge, the oldest sediment should be found at the part of the ocean floor that's farthest away from the modern ridge.
With that in mind, in 1968, the Glomar Challenger went to sea to conduct further tests and gather more data.
In the 60s, the scientific community had realized that we would get tremendous value out of drilling into the ocean floor, that the sedimentary pile on the bottom of the ocean saves the history of the Earth in a way that land sediments never do. They're always being eroded and washed around and reorganized. But once you put it on the passive deep ocean floor, it's saved. And so they all got together and supported this huge project called the Deep Sea Drilling Project, which could go out, hold still in the deep ocean, put down a big long drill string through all that water, and then drill into the rocks and get back the sediments, and also get back a sample of the rocky basement rocks underneath. So when they did that, as soon as the drilling ship was ready to go, this was the very first job it had, was to go out and test seafloor spreading. They went to the South Atlantic, where we knew it was very steady, and they just drilled holes at the center and farther out, and some on the other side to test the symmetry.
The way they wanted to prove the seafloor spreading was very simple, is that they wanted to drill to the basaltic basement, the ocean crust, and age date the oldest sediments that's sitting on top of the basaltic basement. And if seafloor spreading was indeed a viable theory, then at what they were then calling the spreading center, if it was seafloor spreading, that should have the youngest sediments, and then further away you should have the oldest sediments. And they were able to determine this within a few cruises.
A lot of the scientists who were on that drilling ship actually didn't believe in seafloor spreading when they went out there. And when they came back 2 months later, I mean, their feet weren't touching the ground. They were so convinced that it was true.
With the acceptance of seafloor spreading, continental drift suddenly didn't seem like such an impossibility after all. But there was one more piece of the global puzzle that still needed to be put in place. It emerged from work done 3 years earlier by Canadian geophysicist John Tuzo Wilson. Tuzo Wilson had suggested